Hey class, I wanted to talk specifically about weak acid, weak base reactions. We've talked about something similar to this earlier in the quarter when we were looking at solids with acids, but we haven't done it specifically in class with weak acids and weak bases, and I wanted to make sure I fit this in. So what we have here is an example of a weak acid. I wrote acetic acid in its condensed way, so this would be acetic acid. And then I've got ammonia over here. We can think about the stuff we've been talking about in terms of how this behaves like a weak acid, how this behaves like a weak base. And we can see the lone pair is going to be able to accept that proton, so we've got a proton donor, proton acceptor. And the question is, well, what's the equilibrium associated with this? And it's really by looking at a competition between this reaction going forward, how well does acetic acid donate a proton to ammonia, versus how well does it do it backwards. So we can look at how much the reverse reaction is going to happen, where I've got this H plus attached to the ammonia, making it ammonium. I can say, well, how much does this go back this way to establish an equilibrium? And hopefully thinking about it this way, you can kind of see it's going to be how well this thing behaves like an acid versus how well this thing behaves like an acid. This is going to try to donate protons. This is going to try to donate protons. And so we've got a competition of donating protons this way versus donating protons this way. You could alternatively thinking about it in terms of this Ka and this Kb, you're going to get to the same result though. And this is, in my opinion, a little bit more straightforward, a little bit nicer conceptually. So I can think about this in terms of a K for my reaction, which you'll also see it sometimes called K overall or K total. There's a lot of different ways we refer to this K. It's just the K for multiple equilibrium happening. And in this situation, I'm going to be looking at the Ka of my reactants, that's the forward Ka, divided by the Ka of my product, that's the backwards Ka. And remember, if we flip a reaction going backwards instead of forwards, that gets us this flipped 1 over Ka. To make it specific to this reaction, we could write this as Ka for acetic divided by Ka for ammonium. And then I can go ahead and calculate this by looking up the values associated with each thing. Ka for acetic acid is at 1.8 times 10 to the minus 5. Ka for ammonium, I actually have to calculate. So let's go ahead and do that real quick. Since ammonia is a weak base, the Ka for ammonium is not typically written down. It will be Kw divided by Kb. That is going to be 5.55 times 10 to the minus 10. So we can plug that in. And we can calculate what our K reaction is equal to, and then we can do some interpretation of that. So if you're calculating along with me, hopefully you've gotten a value of 3.24 times 10 to the positive 4. Right? And I always like to put the positive. I get so used to dealing with negative exponents when I'm in this class that I like to put the explicit positive. Now, this is a large equilibrium constant, so that means that this reaction is going to go almost completely towards products. I could probably treat this just with stoichiometry, and then do a little bit of a correction backwards like we were doing with our solids at the beginning of the quarter. Kind of makes sense because we've got a weak acid with a weak base, and so we expect that reaction to go forward. Let's look at some other examples of this as well. So here I've got two different reactions, one where I've got the reactions and the products listed, and another where I don't. So take a moment, see if you can determine what the K reaction is for this first reaction. Hopefully you recognize this is acting as my weak acid. Oh, sorry, this is acting as my weak base. This is acting as my weak acid. This is my conjugate. And this is my conjugate base. So I've got two conjugate pairs. And when I look at this, if I'm mixing these two things together, how do I know that this is going to be the products that are possible? Well, HF can donate protons, but it can't accept protons. That would put it into a weird state. H2PO4 could donate or accept protons. So to figure out which one is going to happen, we can look at the Ka values associated with these two compounds, and we can say, okay, which way is this equilibrium going to lie? So for H2PO4, we've got a Ka value, that's 7.2 times 10 to the minus 3. And then I put the Ka for my HF, my reactant acid on top, 6.8 times 10 to the minus 4. And I calculate my K reaction associated with this. And we get a value of 9.44 times 10 to the minus 2. Now, again, interpretation becomes the important part here. I know you can divide two numbers. You can identify weak acids. So the interpretation here is what's going on. Well, this would suggest that when this reaction is finished, when it reaches equilibrium, we're going to have a lot more reactants than products. Right? This would be a reactant-favored situation. However, if we only mix these two things, and we have 0 H3PO4 to start, we know the reaction still has to make a little bit of those products in order to reach equilibrium. So even though this reaction is what we'd call reactant-favored, if we've got no products, the reaction still has to go forward a little bit, but it's going to go forward a very small amount because of the way that H2PO4 HF behave like a weak base and a weak acid. Or rather, how H3PO4 behaves like a weak acid versus how HF behaves like a weak acid. H3PO4 actually donates its protons better, not like a strong acid completely, but it donates its protons enough that the reaction will actually stay mostly reactants, only a small amount of products made. For our last example, we have to be a little bit more careful in terms of what products we are going to predict to make a reasonable reaction. So I've got something that it can act like an acid and a base. I've got something else that can act like an acid and a base. And we've got two options. We can have this acting like an acid donating a proton. We can have this acting like an acid donating a proton. So to figure out what products I'm going to write down, I'm going to look at the Kas of both of these compounds. So the Ka for HS is, well, I'm going to not consider too many things, right? The Ka for HS by itself is 1 times 10 to the minus 17. That thing is a terrible acid. Its Ka value is smaller than water's. So the idea that this thing is going to donate protons is really unlikely, versus our H2PO4 over here, which has a Ka value of 6.3 times 10 to the minus 8. And this brings up a relatively important thing that's going to come up in your organic chemistry classes, which is the strongest acid will react with the strongest base. If I calculate the Kb's for these things, I can see that this thing is going to act very nicely like a base. This thing is going to act very nicely as a weak acid, not quite as well as a base. So my strongest acid present will react with my strongest base present. And I would predict HPO4 2 minus plus H2S. And after I make that prediction, I can go ahead and do a calculation. This thing over here, my product acid, has a Ka of 9 times 10 to the minus 8. So when I take my K reaction, I'm going to have 6.3 times 10 to the minus 8 divided by 9 times 10 to the minus 8. And I calculate. And I get 0.7. Pretty strong equilibrium. We wouldn't call this like this isn't going to go completely towards products. This is one of those really awkward cases where it's mostly towards, is a lot towards products, but not completely towards products. It's still a lot of products and reactants, right? It's almost one. It's almost going to be balanced products and reactants. So what would have happened if we made the other prediction? If we make the other prediction, H2PO4 minus plus HS minus goes to, we have H2PO4 with HS minus. We're saying if we treated this thing as acting like the acid and donating its proton, which is pretty unlikely, we'd have this Ka of 1 times 10 to the minus 17. This H3PO4 has a Ka of 7.23. 7.2 times 10 to the minus 3. And if I calculate my K reaction for this situation, I'm going to have 1 times 10 to the minus 17 divided by 7.2 times 10 to the minus 3. We get 1.38 times 10 to the minus 15. So when I look at this and I say, okay, well, which of this, is this reaction in green or this reaction in orange more likely to happen? This thing, with its larger equilibrium constant, is going to be the reaction that's more likely to happen. This, with an equilibrium constant of 10 to the minus 15, this type of thing isn't going to happen. My S2 minus is such a strong proton acceptor, acts so well like a base, that this would push just backwards. So at its core, mathematically, all we're doing is identifying what is my reactant acid, what is my base acid. I'm taking a ratio of those Kas to see how much it's going forward and backwards, and I get a number. The important part here is then how do we interpret that number in terms of what does it mean to go towards products or towards reactants. We saw that for 2 cases, and then for this last example, we also saw how can we use this idea to start predicting what reaction is going to happen, which thing is most likely to act like an acid or a base.